Okay, so let's continue with chapter 7, integrated processes. Again, sorry for the delay. So this was, in particular, I mean, we have the definition for integrated processes, obviously. So which were not stationary, and we look at some special cases. Now, first off, we look at the armor process. Okay, so then we have the following representation. Okay, so that's going to be the next one. Okay, so here again we already see some problems, and now we're going to look at some special cases. Okay, so this is going to be a remark. Okay, so in case, let's say, the process, okay, is an armor process, okay, and you have P and Q as the orders, okay. So this means, let's say, that the following equation holds, okay. So in this case, we have the following representation. So we have the lag polynomial, which I call alpha here this time, and not capital A. So it calls alpha. So alpha times yt is going to be the lag polynomial representing the autoregressive part of the process y. And of course, here you have the constant plus b, okay, which is the lag polynomial for the noises. Okay, so here in this case, of course, we have that alpha is going to be equal to, and this is going to be 1 minus alpha 1 times L minus alpha 1 times alpha 2 times L squared, okay, minus blah blah blah. So here you have alpha p times L to the power of p and b of L, which is going to be equal to 1 plus b1 times L plus blah 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 plus bq times L to the power of q. Okay, so this is just a representation. Again, here I call the lag polynomial of the autoregressive part alpha instead of capital A. You're going to see why. Okay, so here in this case, because we have this following, if so y is also an integrated process of order 1, so the first order integrated process, then we have the following implications. So first off, the first one is going to be that basically, if you put 1 into the polynomial of the autoregressive part, then you're going to get 0 as a result. Okay? So here in this case, we'll basically say that this is the root of the lag polynomial. So basically, we say that, okay, so i.e., this is going to be that here we have 1 is a root of the lag polynomial alpha, okay? Meaning that basically we say that the process has a unit root, okay? So meaning that y has a unit root, okay? This is going to be it, okay? So this is how we say it. So we use basically the expressions unit root, okay, and integrated of order 1 synonymously, okay? So these are synonymous expressions, okay? So if you say the process has a unit root, then basically it means that it is integrated of order 1 in that case, okay, due to that expression. Again, maybe remember, so in this case, the sum of the total roots basically, okay, have to be less than 1. You know that, right? So for armor process, and here in this case, 1 is already a root of the process. So in this case, it will not work anymore. So the process is not stationary, of course. Okay. So basically, meaning that the process has a unit root is actually that basically 1 is a root of the lag polynomial here. Okay. That's the meaning of it, and that's why we use the expression synonymously. Okay. So basically, I mean, this is just, a convention. All right, now we say that basically, okay, so this is going to be the first part, and the second part is, which we can also show, that the lag polynomial alpha, okay, can be written as follows in this case. Okay, so here we have basically that alpha can be written as, and this is what you will have. Okay, so this is a polynomial. Maybe I'm not sure whether or not you're familiar with that statement, but if, let's say, if you have a polynomial, if you have a root of the polynomial, then you can factorize it. So here we have 1 minus L times another polynomial. Okay, so where basically alpha is, or capital A, so is also a polynomial. Okay, so where basically capital A is a polynomial satisfying the following equation. Okay, so basically it can be written like this. Okay, now if in that matter, so if alpha is a polynomial of order p, then capital A will be a polynomial of order p minus 1. Okay, obviously. So here in this case you can write it like that. So 1, this is going to be 1 minus a1 times L for some coefficients minus a2 times L squared minus and so forth, and then you have, okay, so the last one is going to be AP minus 1, okay, so that's the index here, okay, so AP minus 1 times L to the power of P minus 1, okay, so that's basically the order here of the polynomial. So this is a representation. That is basic analysis, guys, because here you can see that, of course, 1 is a root of here of the polynomial, so if you put here 1, then you're going to get 0 here as this factor. So 0 times something is going to be 0 at all times. So 1 is going to be a root of that. And if a polynomial has a root, then basically it can be factorized by means of 2 polynomials. And here you have the second one. So that's going to be of order p minus 1, obviously. Okay. And of course, what we have is that the coefficients. Okay. So these coefficients, a1, a2, x, and so forth, and AP minus 1 satisfy stationary conditions. Okay. Okay. So because these things can be breaking down, okay, in terms of the stationarity. Why is that? Because the process is integrated of order 1. So if you differentiate the process one time, basically, okay, so just one time, then you're going to get that basically that this is, the process is going to be stationary, okay. So I mean, okay, so let me just explain this why it is. So I mean, here you have the explanation. Okay, so the example, so let's say if you have basically the process is of integrated of order 1, then this implies that the difference of the process is integrated of order 0. Okay, so that's basically the definition of an integrated process. So this is a difference operator. Okay, and a difference operator, okay, can be written as 1 minus L, obviously. Okay, so if the process, I mean, it's, you know, obviously we have, you know, I mean, this representation. So if the process is, okay, so as you write it, so the lag polynomial times y, okay, then here you're going to have that basically, okay, so here you have the difference operator. So this is going to be obviously 1 minus L times A of L times y, okay, or to be precise, by t, of course, okay. So, and this is basically the difference operator here, okay. So this is the difference operator here for this process, okay. All right. Now, since the process here yt is going to be, the difference here is going to be stationary, then you will find that basically that the corresponding polynomial capital A, sorry, we're going to satisfy stationary conditions here automatically. Okay, so that is not a surprise. Okay, again, the process is basically integrated of order 1. So if it was integrated of order 2 or higher orders, then it would not be the case automatically. But here in this case, it is. Okay, so this is just the representation here, and that's the difference operator. So basically, I mean, this is what you're going to get here afterwards. Okay, so that's the explanation. I mean, this is not a proof, but this is the explanation why the process here, okay, or the corresponding lag polynomial will satisfy stationary conditions. In particular, the sum of the absolute values of the roots are going to be less than 1. That's the maybe the property that you remember. Okay, so now we're gonna look at some unit root testing, but we'll consider also another definition, which is transstationarity. Okay, so a process is called transstationarity. So Y is transstationary. So is called transstationary. If it can be written in terms of a stationary process, okay, so Y, here you have that this is going to be delta times t, so you have a linear trend. This is the linear trend here, okay. This is a linear trend here in the data, and then plus here you say, let's say ET, and ET is going to be a stationary process. Okay, so where basically E is a stationary process. Okay, so basically you have a stationary process around a linear trend. Of course, this process is not stationary because, again, so the expectation here of the process depends on t in most cases. Okay. But if, let's say, the process is stationary, which means that it has a constant mean, so in that case, if it has a constant mean, then the expectation depends on basically on t. But if you eliminate the linear trend in the data, then the process will be stationary. So how does that look like if you have, let's say, a time series of a stationary process around a linear trend? So let's say you have, for instance, this is going to be t, all right? And let's say you have delta t. Delta t is going to be a linear trend, so let's say it looks like this. Okay, so delta t is a linear function. Okay, like here in this case, I mean, in particular, it evolves here from the origin of the coordinate system, so you have delta t. Okay, sometimes you have a constant, but sometimes you don't. Okay, here in this case you don't. So, and then basically you have a stationary process around that. Okay, so this is what you would get as a result. Okay, so here it could look like this. Okay, something like that. Okay, so basically you have a process with, let's say, a constant variance around that linear trend, and the expectation corresponds to basically to the linear trend as well. Okay, so you have a trend and transstationary process around the linear trend. Okay, so transstationary process. Okay, so this is a transstationary process. Okay, around a linear trend. Okay, so that's what you're going to get. Okay, so this is, let's say, a typical pattern of a time series that you would identify as a transstationary process. Okay. Now, if that process is transstationary, okay, then we have the following. So the problem here is that if you differentiate that process, you're going to get here, I mean, the difference here of the noise. So let me just continue with that. So let's say if you have to, is that if y is transstationary, okay, then for the difference here of the process, I mean, delta yt is going to be, of course, yt minus yt minus 1. So obviously you would have delta t plus et minus, and then I put this in parentheses, delta t minus 1 times et minus 1, obviously. Okay? Alright. Maybe it just should write a little bit clearer. So here you have delta times t minus 1, okay, and then plus et minus 1. So, I mean, if you have delta t minus delta t times delta times t minus 1, then you're going to get, of course, delta as a result. So this is going to be delta, and here you have et minus 1 is going to be equal to delta et, of course. Okay, so that's going to be the difference here of the process. Now, as you might see, this process here is an over-differentiated process. Okay, so this is over-differentiated, right? That process, obviously. Okay, so that implies, and since this is a constant, that the long-run variance here of that process, of that one, is going to be equal to 0. Okay? All right? That's you're going to see here in the problem. So here, this implies here, okay, so again, that the long-run variance of the process is going to be equal to 0, obviously. We have seen this quite a lot of times, okay? All right? So basically the definitions here in terms of integrated processes don't work. And the problem here of that is, of course, that the process is not stationary, as you might see it here. Okay? So this is an over-differentiated process, so this will basically result in a long-run variance for the process, which is going to be 0. Okay? That is quite obvious. Okay? Now, on the other hand, I mean, if let's say, if basically y is integrated of order 1, so let's say this is what you have and notation, then the representation here of the process, okay, so then it's going to be like this. So the difference here of the process will be like this. So you have delta plus et, and in that case here you have the stationary process. Okay, so if the difference of the process is stationary, then basically you have that, I mean, for the first time, let's say, and with a positive long-run variance, sorry, then you're going to get that basically that the process is integrated to 41. Okay, so that's the difference between the two. So here in this case, this will imply, on the other hand, that the long-run variance of the process is going to be strictly greater than 0. Okay, it's going to be finite, but it's going to be strictly greater than 0, of course. Okay, so that's how you distinguish between the two. Okay, so again, let me just summarize that. Okay, so here in this case, you have a transstationary process. Okay, and here in this case, you're going to get an integrated process. Okay, so if the process is integrated of order 1, then its difference going to have these properties that we'll basically have seen before. And if the process is transstationary, then the process is going to look like this. Okay, so you have basically an over-differentiated part here of the process, so your constant plus an over-differentiated part. Okay, so that's basically how you would distinguish between the two. Okay, now we will establish some tests. Okay, regarding unit roots, because I will wish to figure out in most cases whether or not the process has a unit root or not. Okay, so this is going to be the next chapter. Okay, so next subchapter here, and this is what I'm going to consider. So basically, the question is, how do you test for unit roots? Okay, and that's what we're going to look at now. Consider, and this is chapter 7.2, okay? So that's going to be chapter 7.2, unit root testing, okay? So, how does it work, okay? Now consider, for instance, the regression. And let's say, for instance, you have the following regression model. So let's say you have yt, and then which is equal to rho times yt minus 1, okay, plus epsilon t, okay, and of course epsilon t shall be a white noise by assumption, okay. All right. Now, if you, let's say, you wish to, okay, so subtract, for instance, okay, so an alternative representation will be, if you subtract, let's say, yt minus 1 on both sides here of the equation, okay, then this is going to be an equivalent representation, okay, so what you're going to get here is, of course, if you have yt minus 1, then you're going to get delta yt, okay, on the left-hand side of the equation. And on the right-hand side of the equation, you're going to get rho times yt minus 1 minus yt minus 1. And so if you factorize yt minus 1, then you're going to get rho minus 1 times yt minus 1 plus the noise, okay? And if you say that this is another constant, okay, so for instance, let's say this is going to be equal to phi or something, okay, so that is something that you can say here. So that shall be equal to phi, okay. Then you have an alternative representation. So you have the representation that the difference here is equal to, and then you have phi times yt minus 1 plus the noise, okay. So again, these two representations here of the process, so I'm talking about this one, okay, and this one, are going to be equivalent, okay. So if you, let's say, perform a regression analysis where yt is the dependent variable and yt minus 1 is the explanatory variable, and then you estimate the coefficient rho, let's say, then you're going to get an equivalent regression if you, let's say that the dependent variable is going to be the difference here of the process and the explanatory variable is going to be yt minus 1. So of course you estimate another coefficient, okay, obviously, but if you add 1 to that coefficient, of course, so here I mean, this is just relatively easy to see that if you have the coefficient, let's say, 5, okay, and then you add 1, then you're going to get the coefficient rho, which is here from the first regression, okay, so that's, let's say, the first regression, and that is, let's say, another one, so both two are equivalent, because if you add 1 here to that coefficient, then you're going to get rho as a result, okay. So as soon as you perform one regression, you will get another one too, okay, immediately. So if you perform that regression, then you will basically get this coefficient, and if you subtract 1, then you're going to get 5. And if you perform this regression, you're going to get 5. So if you have 5 and then you add plus 1 here to that, then you're going to get the other one, okay? So no matter what kind of regression you perform, you're always going to get the other one too. Is that something that makes sense to you? So both cases are equivalent to each other, okay? So I'm looking at the two separately. So you can either take that one or that one, it doesn't matter, okay? And testing basically for unit roots, okay, for, let's say, integrated processes, involves basically tests on either this coefficient or on this coefficient, right? So the coefficient phi, okay? Right? So because here in this case you will see that if phi is equal to 0, then you have the difference, okay, of the process is going to be equal to the noise. And if the difference of the process is equal to the noise, then basically you're going to get that the difference is of integrated of order 1. Okay, so let's say, and I'm going to add here this to it. So if, let's say, here for the second part, if phi is equal to 0, okay, then what you will have is that the difference here of the process y is going to be equal to the noise, obviously. So far so good. Now if that's equal to the noise, then basically you will have that the difference here of the process is integrated of order 0. Okay, if the difference here of the process is integrated of order 0, then basically this means, okay, equivalently, that the process itself is integrated of order 1. Okay, so that's basically how the corresponding test will be about. Okay, so either you test 5 for 0, okay, or what you can also do is basically you can also test this process for 1, okay, because in that case, if this coefficient here for 1, so if rho is equal to 1, then you're going to get that this process here is a random walk, okay, right? So that process is going to be a random walk, okay, so then this is going to be the same thing. So if, let's say, rho is going to be equal to 1, then basically we will have that y is going to be a random walk, and that implies also that this is going to be integrated of order 1, which is equivalent to the fact that the difference of the process is integrated of order 0. So either, I mean, you can look either this way, as I said before, from the perspective of the second regression, or this way from the perspective here of the first one, okay? Again, so this is how it works, obviously, okay? So both statements basically are equivalent, okay? So in that case, you will say that, basically, I mean, you can say that, this implies, and let me just summarize that, okay? So here you said that if phi is equal to 0, okay, then basically you have that rho is equal to 1, and if rho is equal to 1, then it's going to be also that phi is equal to 0. So these two statements are, of course, equivalent, okay? One implies the other, okay? All right? But I'm looking at both cases separately, so you have two versions, basically, okay? You can choose whether you like this one or this one. Basically, I think the second part is more common because it tests for 0, right? So that is more intuitive here at the first sight. But I'm not sure. Maybe you see that here. If rho is equal to 1, you have a random walk, okay? Because in that case, the autoregressive model is not stationary, of course. Okay. All right. So I think the second one is more common, but it depends. Okay. So basically, what you have, okay, so this is going to be the Null hypothesis, okay. So the Null hypothesis means that basically, okay, so if that's the Null hypothesis, we will say, okay, so testing for unit roots, okay, means, okay, basically, okay, for a unit root, means, okay, testing basically the corresponding Null hypotheses, and that's going to be as follows, okay. So basically, it will be that, okay. So the first, okay, for the first regression, it's going to be looking like this. So the Null hypothesis is that rho is equal to 1, all right? And the alternative is that basically the process is stationary, right? So the process has a unit root, okay? So meaning that here y has a unit root, okay? In this case, obviously. And on the other hand, if you can clearly see that if basically the absolute value of the process, of the coefficient is less than 1, then basically the process is going to be stationary. I'm not sure whether you remember this or not. So this is the first order autoregressive process, and the first order autoregressive process is stationary if and only if the slope coefficient here, okay, has an absolute value which is less than 1. Maybe remember that. If it's greater than 1, then it's not stationary at all. Okay, and it's not even integrated for the 1. So the alternative hypothesis will be that the absolute value here of the process, okay, so the absolute value of the process is less than 1. Okay, so here that's going to be the alternative. Again, we will not look at the case where basically that the absolute value here of the coefficient is greater than 1, because if the absolute value of the process of the coefficient is greater than 1, then the process is going to be more or less, I mean, it's going to explode here in that case. So an observation here for that, okay, so just for you to know, the observation here for the process will look like this. Okay, so sooner or later, the process will look like this. Okay, it goes so quickly that basically I mean, and after the second or the third observation whatsoever, the process is going to explode. So here for that case, if let's say the coefficient has an absolute value which is strictly greater than 1, okay, so in that case we don't need to look at that. So in here, for instance, I mean, in this setup will mean that the process here is stationary. So that's going to be the first part. Okay. Now the second part is basically similar. Okay. You got a question?
Yeah. What if we set the alternative hypothesis to like rho is not equal to 1, or is it just?
No, I mean, as in this case, okay, so that would be, but here from the practical perspective, okay. Again, so what would happen, let's say, again, so this is what I want to try to explain. What would happen if the coefficient is greater than 1? So let's say, for instance, you just consider the following example. You don't need to write it down, so but consider the following example. So let's say, for instance, yt is equal to 2 times yt minus 1 plus the noise. Okay? So how that, I mean, the question is, how would such a process would look like? Okay? That's, you know, that would be basically a question that you might ask. And if you look at the representations here for the first order autoregressive processes, okay, so I think it was from chapter 3, okay, so in this case you would get the following expression. Let me just illustrate this, okay, so for the first order autoregressive process, okay, you will get the following expression here for that. Just let me just add here too. Okay. So it's gonna look like this. Okay. So, and I will use this coefficient here. So basically, I mean, okay, let me just add a little. No, I mean you can look it up. So this is gonna be 2 to the power of t times y0, so the starting value, and then you'll have plus, okay, so the representation here, the sum, that j is equal to 0 till t minus 1, so of 2 to the power of j times the noise. Okay, so that's going to be the noise, as you can see. Alright, so this process tends towards infinity almost surely. That's the thing. Okay? So the realizations here of the process will tend to infinity almost surely. You would recognize this from the time series. So if you simulate such a process, okay, where basically the coefficient is strictly greater than 1, or the absolute value of the coefficient is strictly greater than 1, then you would get a process as a result which will tend to infinity. Okay? So you could try it out. Okay, if you like, but you're gonna get something like this, Okay, so here, of course, I mean, you have a certain starting value, and after a certain point, the process is going to explode. And this is not what you have as an observation here of the time series. So why would you consider that case? Basically, this is not what you have. Okay, so if you reject the null hypothesis, why would you assume that the process looks like that? Okay. That's the reason. So that's why the alternative hypothesis exclude these cases, okay, where basically the process tends to infinity. Okay, that's not what you see in the time series. Never. I mean, if you see that, then you don't need to look at the analysis. I mean, this is not stationary, and that is not even integrated for the work. So you would basically exclude this. Okay, that's the explanation here for that. Okay, so again, so since that process tends to infinity as basically, you know, time converges, okay, because you have, of course, you have the starting value and etc., etc. Okay, so in that case, you will have that. That was, that would be the observation or of the process, and that is something that you won't consider. Okay, so basically, the alternative hypothesis is that the process is stationary. Okay, so y is stationary. And a process that tends towards infinity is not a stationary process, okay, obviously. So that is not what the alternative hypothesis is about, okay, here in this case. All right, now the second part is going to be the similar, okay, so here if you look at the second regression and you test this coefficient for 1, then the meaning is going to be this, and it's going to be the same. So here in this case, you'll have that the Null hypothesis involves basically that, the coefficient phi, sorry, not gamma, I used phi. So phi is going to be equal to 0. So basically meaning the same thing. Okay, so the process has a unit root, so that's what you would have. Okay, so that's going to be the same thing. So y has a unit root, okay, meaning that y is integrated of order 1 again, and the alternative hypothesis in this case, okay, so if you look at some stationary process, okay, so if let's say the alternative, considering the alternative process, you will have that here in this case the alternative will be that, okay, so this is that y, so phi is less than 0, okay, because if phi is greater than 0, then you will basically have the same result, okay. So again, if the absolute value of rho is basically less than 1, then it's equivalent to the fact that basically phi is less than 0. So this, you just have a one-sided test, not a two-sided test. You just have a one-sided test. Okay. So here in this case, okay, meaning that y is stationary. Okay. Okay. So guys, this is a one-sided test. You have to understand this. Okay. Either the process is integrated of order 1, or the process is stationary. And there are basically no other cases here in between. So you just have basically 2 alternatives, not 3. So you have a one-sided test, not a two-sided test. Okay, so this is a one-sided test. Okay? Both. Okay? And the reason being is that, of course, either the process is stationary or it has a unit root. Okay? So that's why you have a one-sided test. Alright? Now, okay, so that's how it's going to work. Okay, so what you will calculate is, of course, you will calculate the test statistics. Okay, so that's going to be you're looking at the t statistics. Okay. And I already told you how to calculate the t-statistic, basically, here from this regression. Okay, so in the first case, okay, so for the first model, okay, so you'll have the t-statistic of the coefficient rho. It's going to be as follows. Okay, so basically, you'll have the estimate. Okay, so the empirical estimate, which you derive from the least square regression, you subtract 1, and then you divide this by the standard error here. Okay, so the standard error, okay, I'm using the notation sigma hat, okay, basically here of the coefficient rho, and this is the standard error. Okay, I already told you how to do this. Okay, so this is the standard error. Okay, standard error here of the coefficient. Okay, so you divide basically rho minus 1 by the standard error, and the standard error of the coefficient rho is going to be also equal to the standard error of the other coefficient, because basically the standard deviation and the corresponding estimate don't change if you perform basically just, you know, a simple addition here on this coefficient. Okay, so I mean, this is the relation here of the coefficient. So if you subtract row from row, 1 minus 1 from row, then you would basically, you get that the standard error is going to be the same. Okay, so that's going to be the test statistic here from the second regression. Okay, so I call this T5. Okay, so because that's going to be basically the test statistic here of the second regression, and that is, of course, you take the corresponding ordinary least square estimate, okay, and then of course you have -0 divided by basically the same expression, so this is going to be the same thing, okay, but the standard errors are going to be equal, so the standard error here for that is going to be equal to the standard error of the other one. Okay, so this is the standard error, okay, of the coefficient phi, okay, which is of course equal to that. Now, the biggest problem here with that is if, and this is very important here, so if basically the process is integrated with order 1, and suppose that the process is integrated with order 1 and then you perform regression here, the problem is that the test statistics do not converge to the normal distribution. Okay? Now, on the one hand, I mean, we have seen this here in the previous section, but I'm going to summarize that. So, okay, so if, let's say, if the process, okay, is stationary, okay, let's say, or integrated with order 0, if the process is stationary, then you would have that basically that the test statistics, okay, so both of them, okay, so T rho and T phi, both converge in distribution to the standard normal distribution. So they will be asymptotically normal. Okay? We had that. So basically you can use normal distribution for that. Let's say if your number of observations are sufficiently large. Or number of observations is sufficiently large, sorry. Okay? So, and that is basically something that you could do. So if the process is stationary, then you can test coefficients regularly. It doesn't matter. But the problem is this: if, and that is going to be an important issue. So I have summarized this by means of the following lemma. Okay. Okay. So if basically if you have that the process is integrated of order 1, okay, then you have seen this in the previous lecture, that there are some weird things going on. So then you'll have basically that these test statistics do not converge in distribution towards the standard normal distribution or to any normal distribution at all. Okay, so then you would basically have, okay, that the test statistics, all right, okay, do not converge in distribution. Okay, to the normal distribution. Okay. And that is very important. So they are not asymptotically normal. Okay, do not. Okay, they do not converge in distribution to the normal distribution. Okay, and that is a problem. That was figured out basically in the 1970s. Okay, by Dickey-Fuller. So in I think 1979 or something, 40 years ago almost. Okay. And there are, of course, asymptotics regarding this issue, so you can, of course, derive, you know, how the distribution look like analytically. But in the first experiment, that was only just a numerical, a Monte Carlo experiment, let's say. Okay, so what they did is they were simulating test statistics, so they were performing, you know, regressions on simulated integrated processes. Okay, so processes with the unit roots, so they were simulating them, and they were performing the regressions, and they were looking at the test statistics, and they just looked at the empirical distribution here of the test statistics that they get from the simulations, and that will, generated, that's how they generated the critical value. And to be honest, that's going to be your next assignment. Okay, so a next or final assignment will be just to repeat that experiment. Okay, so again, all you need to do is just to simulate integrated processes. That's going to be easy. It's not going to be difficult. Okay, and for each of the integrated process, you will have to calculate the corresponding test statistic, either from the first or from the second regression again, so they're both regressions are equivalent. And then what you do is you look at the empirical distribution of the test statistics, and therefore you derive critical values for the corresponding unit root test. Okay, so that's how you would derive the critical values, and that's going to be your final assignment. Okay, I will of course release this. Okay, so you don't have to, but you don't have to submit before Christmas. Don't worry. So you will have time. Okay, you have much more time just to finish that. But you already had basically written. I mean, I had you written a program regarding the estimation. Okay, and of course the test statistics as well. So all you need to do is you take that function, and then you apply on your simulated process that you're going to simulate. So all you need to do is you need to simulate the process and then apply your function that you already have on simulations to get the empirical distributions of the test statistics. Yes, you've got a question?
Yes, I want to ask, like, if we will have any feedbacks on the programs that we will.
Yes, of course you can. Yeah. I'm going to get you some feedback, but I couldn't do it for all of you. So either I have to finish first for all of you, and then you're going to get the feedback first, of course. Okay? So during Christmas, I will test your program and provide you with the feedback, of course. But I couldn't do it. I underestimated the time that it takes for that. So anyway, it's my problem, not yours. You're going to get your grades anyway, but I think it looks good. Anyway, so in most cases, I mean, I looked, at certain programs, and they all worked. So I hope that this will be the case for all of you. Okay. Good. Now, okay. So that's what you will have to do. You just basically extend your second assignment to a third. Okay. And see how the critical values will look like. Okay. Now the distributions that they converge to are called so-called Dickey-Fuller distributions. So that was published by Dickey-Fuller in 1979. Okay, so unit root distribution of estimated autoregressive time series with the unit root. Okay, so the corresponding paper that was published, it was by Dickey-Fuller. Okay, so there were two guys, Dickey and Fuller. Okay. And the corresponding distribution, okay, so 1979, and the corresponding distribution that they generated, okay, was later made after them, okay, so that's called, they follow the so-called Dickey-Fuller distribution, okay. Now, how does the Dickey-Fuller distribution look like? Okay, so how do they basically compare to the normal distribution, okay? So, the standard normal distribution looks like this, okay? And the Dickey-Fuller distribution, this is just a little approximation, it's shifted more towards the left, okay? So it's basically more or less here, okay? So it looks like this somehow, something like that, okay? So the problem here, if you test, if you take the normal distribution for testing the null hypothesis, the problem is that the null hypothesis is rejected way too often, okay? Again, so for instance, let's say the critical value is here, okay? So this is a left-sided test, as you can see this here, because the alternative hypothesis says that basically that the coefficient is less than 0, so this is a left-sided test, okay? So in that case, this is what you would do, okay? So you reject the null hypothesis if, let's say, the critical value is below here a certain point, let's say here, okay? So let's say this is the alpha quantile here of the distribution. Now if you use the normal distribution for that, then you will see here in this picture that you reject the Null hypothesis way too often if you use the normal distribution, okay? Because you would only reject it here, okay? So let's say if that is the 5% quantile, okay? So here you have 5% of the area, okay? So you're supposed to reject the Null hypothesis if the test statistic is less than this value, okay? So I call this is, let's say, the alpha quantile, okay, of the Dickey-Fuller distribution. So meaning that basically that the area here is going to be equal to alpha, okay? And if the test statistic here for the test is below that, meaning that it's less than that, then you would, or you're justified to reject the Null hypothesis. Now, if you use the normal distribution instead, okay, so if you use the normal distribution instead, which have a critical value, let's say here, more to the right, so this is the alpha quantile of the standard normal distribution, basically you will have that, okay, so the area, this area here is of course equal to alpha, but if you use that, then you're gonna reject the Null hypothesis way too often, okay? So you reject the Null hypothesis if you have a test statistic which is here, okay? But you're not supposed to, because you're supposed to reject the Null hypothesis if it's, you know, less than the alpha quantile of the Dickey-Fuller distribution, you understand? Okay? So if the normal distribution is used for testing unit roots, okay, then the Null hypothesis is rejected too often, okay? So the Null hypothesis is rejected too often if the test statistics or the test statistic, because they're equivalent, is assumed to be normal. Okay? So, I mean, what does the Null hypothesis say? The Null hypothesis says that the process has a unit root, you understand? Okay? And that's not the case. Even, you know, if you have a test statistic here. I mean, let's see, not at least not at the 5% level, okay? So if you have a test statistic which is here, okay, then you would reject the Null hypothesis based on the normal distribution, but based on the so-called Dickey-Fuller distribution, you don't reject the Null hypothesis. Okay? You understand this? Okay? And your assignment will be, and then this is something that you can already prepare, so if you like, you can do that. Your assignment will be to generate the critical values, okay, of the Dickey-Fuller distribution. So basically, I will have this picture here as a result, okay, from your simulations. You understand? Okay? So I want to have just the critical values here for the